With our first patient, we get K readings of 43 diopters and 44.75 diopters at 90. The corneal astigmatism for this patient will be the difference between the two readings. So that's 1.75 diopters of astigmatism. When we do refractometry, we get -4 minus 1.75 at 180. So we get 1.75 diopters of cylinder through refractometry, which checks out with our 1.75 diopters of corneal astigmatism we got from keratometry. The other thing to take note of here, though, is in our K readings, the steepness of the cornea is at 90 degrees. That's where it's steeper. So in our prescription with a negative cylinder, our axis is going to be at 180. If we transpose that to positive cylinder, our axis is going to be at 90, just like the steepness of the eye. Okay, that was pretty simple and straightforward. Now for our next patient, we get K readings of 43 and 4350 at 90. The difference is a half a diopter. So what we're getting is a half a diopter of corneal astigmatism for this patient. Then when we do refractometry, we get -3.5 -2 at 180. The cylinder that we get is way different from the degree of corneal astigmatism we got from our keratometry. This person has lenticular astigmatism as well as corneal astigmatism. That means that the crystalline lens is misshapen enough to give 1.5 diopters of astigmatism added to the 0.5 diopters that the cornea is giving is a total of 2 diopters of astigmatism for this patient. Okay, next patient. We get K readings of 43 and 44 at 90. The difference shows us a corneal astigmatism of 1 diopter. Then through refractometry, we get a -3 -1 at 90. So we also get a 1 diopter of cylinder, but it's at 90 degrees. And a negative cylinder to correct corneal astigmatism should be at 180. Okay, in order to show what's going on, first I'm going to transpose this into positive cylinder because we're used to working in positive cylinder. Then I'm going to draw some pictures. I'm going to draw a picture first of the corneal astigmatism. So it's going to look something like this with the steepness at 90 degrees, 1 diopter of astigmatism at 90. It's going to be with the rule, so it's going to be a passing football. Now, normally, we would correct the steepness of the eye at 90 degrees by using a corrective lens that has a steepness the opposite way, at 180 in this case. But our refractometry tells us that we need a lens with an axis at 180. What gives? Now this is getting a little bit confusing because we're going back and forth between positive and negative cylinders, so we're going to draw a power cross. When in doubt, draw a power cross. That is, power crosses are the bridge between negative cylinder and positive cylinder. Okay, what I'm doing first is just the cylinder part of the power cross. This is not a full power cross. This is just the cylinder. So our axis is at 180, and of course the axis has no power, and the opposite 90 degrees has our +1 power. The answer here is in the crystalline lens. The crystalline lens is misshapen so that it has a power meridian at the 180 and an axis at the 90. Okay. It in fact has 2 diopters of lenticular astigmatism at the 180, one of which neutralizes the 1 diopter of corneal astigmatism at the 90 and leaves 1 diopter of lenticular astigmatism at the 180 that needs to be corrected with a corrective lens. Okay, our contact lens prescription also needs to include a base curve. And the way to figure out that is you take the flattest meridian of the cornea, the K reading, and you want to go 3 or 4 diopters flatter and work with that number. But you want to express that number in millimeters of radius. What does that mean? Okay, remember the radius of curvature formula? We need to know the dioptric power, that's the K reading, and we need to know N is the refractive index, in this case of the cornea. And the refractive index of the cornea is 1.3376, and the K reading that we're going to use for this particular patient is 44. We're just going to plug the numbers into the formula, solve, and we end up with 7.67 millimeters radius. But remember when I said at the beginning that we're going to use 3 to 4 diopters lower? The power we're actually going to use in our formula to find the correct base curve for this patient is 40 rather than 44. We're going to go 4 diopters lower. We're going to solve and we come out with 8.44 millimeters is the base curve. You really don't have to worry about being able to figure this out on paper and find the base curve, because as long as you know the K readings, there are plenty of charts that will tell you the radius in millimeters and the base curves to use. So you'll rely on a chart probably, but I just want you to know where this came from so you know what you're doing. Now, when you look at contacts, I'll show you my contacts, and this is where you will find the base curve. It'll look something like this. It may not be 8.4, but it'll look something like this when you're looking for it. Corneas with K readings under 42 are considered flat. From 42 to 44 considered average, and over 44 are considered steep. Flatter corneas are going to require base curves from around 8.8 to 9. Average 8.4 to 8.6, and the steeper are going to need base curves from like 8.1 to 8.3. The packaging of these contact lenses also shows the dioptric power. And there's 2 things that I want to go over about the power before I end this video. And I've talked about both of them in prior videos, so they're not really new, but they are important. One is spherical equivalent and the other one is the vertex distance. Okay, for this patient we have K readings of 41.5 and 42 at 90. Refractometry minus 325 plus 0.5 at 90. The base curve, like I said, we're not going to figure it out mathematically. We're just going to look at a chart. But what you do need to know is when you look at the K readings, you're going to take the flatter one. That's what we're going to go by. And the flatter one is 41.5. And that is also, we also know that that is a flat cornea because it's under 42. So the base curve will be something like 8.8. Now for the power, we're going to give this patient a spherical lens, and they have a certain degree of astigmatism. So what we have to do is figure out the spherical equivalent. The spherical equivalent, remember, is the sphere power plus half of the cylinder power. Okay, next patient. We did refractometry on this patient, and they are a -5 spherical. Now, -5 refractometry, we're about 10 millimeters, about a centimeter vertex distance. Now, but the contact lens sits right on the eye, so we need to compensate for the vertex. This formula here, and I don't believe I introduced this in the videos prior, this formula is called the approximate formula method. The small d is the change in vertex distance in millimeters. So in this case, I said 1 centimeter or 10 millimeters. The capital D, of course, is the power that we got in refractometry. So that's a -5, and we square that. So that's going to be a positive 25. So our change in power is a quarter of a diopter. We want to change it a quarter of a diopter. Now the question is, are we going to make that -5.25 or are we going to make that -4.75? Don't forget our mnemonic, cap, closer, add, plus. So as we're moving it closer, if we're adding plus, that means we're removing minus. Okay, one last thing. I'm not going to go over diameter of the lenses in this video. It's just too darn long. That's really the only reason. When we talk about the gas permeable lenses, there's a lot more to talk about as far as the diameter. So we'll also discuss how it affects the prescribing of soft lenses in another video. But I just wanted you to see the packaging where you might find the diameter and what it looks like. And that's it for this one. Thanks for watching.